Welcome to module 6 lecture 3. If you recall, we discussed about factors affecting strength of concrete in the last two lectures of this module, and we also said that it is the test condition that has a role on the value or on the estimated strength that we get, estimated cube strength or cylinder strength that we get from our tests. So, what are the factors related to test condition that affects these test results are is what we are going to look at today, right. So, it is essentially we are looking at what are the factors and how do they factors, what are the factors and how do they affect the strength, the test condition, test related factors that affect the strength, statutory factors, those will be affecting the strength. So, general outline, compressive strength, the factors which affect the compressive strengths are end condition and capping of the sample or the sample of the specimen that I take, size and shape and aspect ratio of the specimen, rate of loading, and then we will look into some of these aspects related to tensile testing, some of the aspects related to tensile strength testing. So, compressive test, compressive strength, test for compressive strength actually what we do, let us take a cube and we apply load from top and bottom to a machine, testing machine, where this load is applied through hydraulic system, and we can also control the rate of loading, etcetera, etcetera. So, we apply load like this and we define the strength as P max by A, that is a simple way of doing that, and test condition induces variation in results, that is what we are going to see. Of course, therefore, I must have a standard test condition. Now, if you recall some time earlier we talked about that the cube strength that you get actually is not really a measure of the strength that you get in the structure, because several factors would be affecting the strength in the structure as well as that obtained from the cube test, and they are not same. The factors, values of those factors or levels of those factors are not same, but then it gives us a relative measure. It gives us a relative measure of the materials that has gone in concrete making. Since the test condition affects my strength, I must standardize this test condition and use the same test condition for all the cubes, so that I can only compare the materials. So, standard test condition is given in codes. In Indian scenario, it is given in IS 516, originally framed in 1959 or so, but then it has been reaffirmed last possibly sometime in 2009 or so, right. So, it remains same, still remains same. So, what we do, we apply load from the top, uniformly distributed load on the cube surface, and bottom there is an uniformly distributed we assume that there is an uniformly distributed reaction from the machine frame or machine plate as we call it. We apply the load also through the machine plate, and as we apply, the reaction comes from the bottom and the concrete cube is crushed under those two loads, all right. So, that is how we test cube, but we can test a part of a beam as well, we can test the part of a beam as well, all right. We can test the part of a beam as well. So, for example, this is the whole beam, this is the whole beam, this is the whole beam, this is a beam, part of a beam. After doing flexural strength on the test for flexural strength on a beam, we will discuss this test for flexural strength sometime later. After doing that test, the remaining portion, unbroken portion, actually I can test under compression. So, the load is applied through this and bottom plate is here. So, applied through the top plate, and then as we press it goes down and I get some results. Remember, this results is not the same thing. IS 516 gives test on portion of a beam is not same as the cube, is not same as a, and these two things are not same, they are not same. They give you some, this gives you some strength, the other one gives you some other strength. But anyway, that is good enough for our purpose. We have, because we are relatively comparing. So, compare these results with only the beam results, compare cube strength result with only the cube strength result. Now, this is not so popular, while cube is very, very popular. Cube is most popular and commonly used. This is rarely used actually. Now, end condition in capping. End of test specimen shall be truly plane, first of all, this should be truly plane. This is what we talked of. Now, this should be truly plane actually. This should be truly plane. This portion should be truly plane. This should be truly plane. Otherwise, the undulation, the contact area would reduce and there will be stress concentration, So, effective contact area will reduce and apparent strength will reduce. So, therefore, this must be, first thing is it must be plane. And to do that, what we do? What we do is we cast surface cast against steel mold are smooth, and therefore, it does not require any treatment. I will talk about capping a little bit later on, but it does not require any treatment. It is very smooth, and I put that below the loading plates, what we call loading platens. So, I put this one, this top portion, this portion is this portion, this portion I am talking of. It is that one which was in contact with the steel mold during casting and not exposed to air. So, this will remain by and large plane if my molds are standardized and properly made within tolerances, then this will remain plane. While we can do this for cubes, well, cylinder actually you cast in this manner, cylinder you cast like this, So, this surface is always exposed. So, this surface is always exposed, this surface is always exposed, this surface is exposed. So, we apply load however through this. So, anyway, cylinder scenario we can't apply, but we have to see that it is sufficiently smooth, there is no variation, right. Now, that is as far as cubes and cylinders, largely cubes are concerned. But if you cut a core from actual structure, sometime we do that, we will not be, right now we will not be discussing this, but sometime we cut a core from the, cut a core and from the structure. So, this is a core actually, this is a core cut, cut core from the structure, which you have seen in the beginning, first lecture, if you remember, I actually showed you a core. So, we cut a core from the structure, and this core sometime may have rough surfaces, and or length may not be sufficient. You have to have a specified length depending upon the diameter d. So, L by d. So, there is a minimum L by d which is 1, but supposing I have got slightly less, then I might do some sort of a capping here. That means, put some materials and do capping, So, if you do this kind of capping, you will see that the results in variation in the strength. So, that is what we are saying. So, end capping results in strength variation, right. End capping results in strength variation. Now, this variation or the difference that we get is attributed to lateral expansion of capping material and concrete. Relative, is both will be, the capping material can be expanding. So, what you are doing when you are applying load like this, on this one you are applying load like this, material here would be actually expanding, So, if you put a capping material here, this will also expand and concrete will also expand. So, it is related to this sort of expansion of this capping material and concrete. Let us see how it is. So, we will see that right now, we will see that right now, we will see that right now how it affects. Supposing I put different capping material, let us say first is this is alumina cement, first one is the alumina cement, this one is the alumina cement. So, I have made actually cubes or cylinder like this, and I am using different capping material here. They might be this might be rough, this may not have been smooth, etc. I am using different or whichever way, this is a result of experimental results. So, I am actually doing some capping and capping here, put this capping, and first material that I am talking of is alumina cement. So, this is alumina cement, and second one is gypsum plaster, third one is another gypsum plaster, fourth one is sulfur with filler, sulfur concrete with some filler, sulfur actually colloidal sulfur, yellow sulfur you might have seen it actually melts. So, you put some aggregate into it, some filler, then it becomes almost concrete when it solidifies. So, the sulfur concrete. So, I can put some sulfur, plaster of Paris, calcium sulphate 2H2O that we know, and POP plaster of Paris with ordinary Portland cement. So, plaster of Paris is this, ordinary Portland cement is here, 6 is sulfur, 6 is sulfur, 5 was same as sulfur with filler and is pure sulfur, 6 is right. So, you see if you have different capping materials, same cubes or same cylinder, if you look at relative strength, if I assume that high alumina cement gives me 100% strength, for strong concrete it goes on reducing with the capping material, and for weak concrete the effect is somewhat less, in fact you find slight increase. Well, this is a qualitative statement, I am not doing quantitative statement, qualitative statement. So, what we observe is that there is a variation and it depends upon the type of capping that you are using. So, end capping has an effect on end condition. Normally, if you do not have a capping, the machine plates are straight away coming in contact with, top and bottom, which are usually steel. So, you have steel plates, they come in contact with the specimen itself, I mean the sample specimen itself, all right. So, specimen itself, so that comes in specimen itself, all right, not sample, specimen, because sample would be a couple of specimen would make sample. So, it specimen from the sample actually. So, specimen Q specimen itself, all right. So, this is what is happening, machine plates coming, and if you put depending upon strong or weak concrete, the F factor will depend. So, you see it depends both on the strength of the concrete, the quality of the concrete, as well as the effect of the capping material is a function of the strength of concrete again. It is a kind of non-linear situation. So, that is what it is, and therefore, this is an important issue. So, end condition and capping, this is an important issue. Now, what is the mechanism? Let us see if I have some diagram, some diagram right now I do not have perhaps. So, no problem. So, what okay, yeah, but explanation is there. Let me use my own diagram, right, Okay, the observation is, I mean, or let me first use this my diagram and then I will come back to. Now, this is your cube, you are applying load like this, and we have discussed that my material will have a tendency under this compressive uniaxial compressive situation, it will have a tendency to move along this direction as well as along this two transverse direction. Now, if it tries to move along this direction, that means, it finally the failure is because of tension, then the movement is important, movement of this material along this direction is important. Now, this point, the movement of the material is restricted by the friction between the machine plate and the specimen. So, there is a kind of a force acting like this, frictional force, which will not allow this movement. Similarly, here this is a kind of a frictional force which will not allow it to move along this direction. So, this is the surface, but then surface material is in contact with the just bottom next layer of concrete. So, if there is a force acting and it is trying to contract, let us say trying to expand, it would also try to take the material below, but if there is a force opposing this, this also will be opposed somewhat, but it would gradually get reduced, gradually get reduced. There is some sort of opposition to the movement here also, but gradually it will get reduced. In other words, your this forces, resisting forces, I mean it would get reduced somewhat. So, you do not have really purely uniaxial situation, you have a situation where there is some sort of a force acting onto the specimen depending upon depending upon the type of specimen or L by D up to some height, this there is a force acting like this also, some height force acting like this also, this will depend upon, this is your L and this is your D, if I may say this is the D is the dimension of the cube. So, if it is D and D, then there is somewhat overlap is there, we will come to that just now. So, you see there is a opposing force or to the movement, horizontal movement or transverse movement, there is opposing force to transverse movement, both this direction as well as in this direction there will be an opposing force. So, this opposing force actually what it would do? It would actually net effect is a force, compressive force acting like this, net effect is at this point compressive force acting like this, compressive force acting like this. So, tension force will be acting normal to the tension force will be acting normal. So, it will act like this and here also it will act like this, no tension will act like this. So, tension acts like this because compression is along this direction, compressive along this direction, net force because of the resultant of the frictional resistance and the applied load. So, net compressive force will be along this direction, which means there is a tensile force, the transverse tensile force because of Poisson's effect will act like this. So, you have a crack in this direction and you have crack in this direction, you have crack in this direction and you have crack in this direction. This is called Platen effect, this is called Platen effect. Okay. Now, supposing I put a material here, I put some material here, I may put some capping material here. Now, machine plate is not in direct contact with the specimen. Machine plate causes the friction is between this and the friction is between, friction is here now between the machine plate, your load is coming from here and friction is somewhere here. So, this material will try to expand in this manner, but would be resisted by the friction. So, it is Poisson's ratio which causes it to deform along the transverse direction, Poisson's ratio along the transverse direction and its stiffness, right, is an important issue. So, if it moves high, moves quite a bit compared to the stiffness, resistance to movement is stiff, it is as a material property for a given force, then for different capping, it supposing I have two different capping, their movement along this one, more it moves, it will cause the concrete to move more along this direction. If it is stiff, then the strain, this directional strain itself will be low, therefore, Poisson's effect will be minimal. So, more the Poisson's ratio of this capping material and less the modulus of elasticity of that material, it will tend to actually nullify the Platen effect more. So, in other words, just let me now put it here, higher nu, where nu is the Poisson's ratio divided by E, modulus of elasticity, stiffness, more modulus of elasticity, more modulus of elasticity is then less will be the movement. So, nu by E is important. If this is less, this term is going to be higher, and if this is more, this term is going to be higher. So, this if this is higher, so higher nu by E induces higher lateral movement, higher nu by E induces higher lateral movement. So, that is what we have understood, that is what we have understood. I am just erasing it out now, right, again erasing it out. So, softer and weak material has higher expansion and their lateral expansion is more than that of concrete. So, softer and weak material has higher expansion and their lateral expansion is more than that of concrete. So, therefore, this will cause, if that moves, concrete will automatically also move, Platen effect will get reduced significantly. Softer and weaker material will reduce. The higher expansion increases lateral move strain in concrete and crack parallel to the load grows rapidly, leading to failure under lower load. So, you see a higher, so that means if a higher nu by E material as a capping material, that is softer and weak material, you put it as a capping material, it will cause, it will itself expand and will not restrain the expansion of concrete under the Poisson's effect, and therefore, concrete vertical cracks you will see possibly crack parallel to the load, that is downward load. So, crack will be parallel vertical load, vertical cracks, and that would failure will progress under that kind of load. Okay. For strong capping material, result is opposite obviously. So, if the nu by E is small, that means this material itself has low Poisson's ratio and E is high, very stiff, therefore, stronger material has this kind of behavior and that would actually restrain, and therefore, it would show a higher strength compared to the one with higher value of nu by E, because it will restrain. So, the net effect is the material is not going to expand in the transverse direction, there is a restraint to that. So, net effect is you will require higher load to cause it to now fail. So, this is the effect of end capping, as we have seen. The end platens of the machine produces same effect as strong capping material. So, the capping end platens, machine platens, because steel is a material, it is a strong material and its Poisson's ratio is divided by modulus of elasticity is relatively low if there is no capping material. Therefore, plate restricts the movement and increases apparent strength, and the degree of restraint depends on friction between plates and the concrete surface. So, that is why everything has to be standardized. You see, you have to standardize your plate, and whether you go to use a capping material or not, that has to be standardized. Normal Q's test, we do not apply any capping material, but wearing this capping material we did understand why possibly a specimen which has got high L by D fails at lower load compared to a specimen which has L by D equals to 1. So, the degree of restraint depends on friction between plates and concrete surface, and for very low restraint capping material, wax, let us say if we put wax, the difference is quite evident from the cracking pattern. We put wax which is a very low restraint, it does not restrain because it is very low strength, weak material expands quite a lot and therefore, you can find almost vertical cracks, right. Something similar, for example, rubber or Teflon, if you use, it has got a high strength, but low stiffness. So, it allows expansion, but does not fail itself, and therefore, you will find again the effect of the plates are gone. There is something called brush platens, made of plates made of brush, you have brush, closely placed brush platen. So, you use below the plate a brush. So, brush can expand easily, it is a brush, steel brush, you just put that, it can expand, although it will not fail. So, that is it, that is so that is Platen effect basically. So, if you see, if you have no effect, no capping, no restraint practically, and if you have high restraint, then these are the scenario: low restraint, high restraint. High restraint you will get, because as I told you that net compression, net compression will be along this direction, resultant force. So, transverse tension will act like this and you have something of this kind, while if you have low restraint, basically wax or something or Teflon or brush Platen effect, brush plate, then cracks would be vertical because of the failure due to Poisson's effect. So, this aspect is to taken into account. So, therefore, we got, if you recall, we got failure of the cube like this. This is the cube failure. If you remember, this is what we showed earlier. In the beginning, cracks will come like this, then this is the shape that you get, and some cases you go further, you might get a shape like this. This is the portion which does not get failed, right. So, this is the final portion. So, Platon effect act like this. Due to the Platon effect, it is it is like this, but then restrictive effect is limited up to certain distance from the plate. As I said, it is limited. If this is your specimen, what is important is L by D. So, up to certain portion this is effective. This Platon effect, this will act up to certain point, right. It will act up to certain point, does not act full length. So, this act up to certain point, right. This act up to certain point. Okay. So, in this direction also it will be there. So, it will act like this. Now, how much is this distance? This distance is seen to be, it is related to this d, this can be related to this d. So, it has been observed that up to about 3 by 2, 3 by 2 maybe H6 d, 3 by 2 d, up to this d, the end of the cylinder diameter thus. So, it is actually estimated actually up to 8.6 d, this effect will be there. So, if this is d, 0.86 d, this distance will be 0.86 d, sorry 86 d, 0.86 d. This side also 0.86 d, this side also 0.86 d. So, you have L equals to d, which is the case for cube, actually there is an overlap of the Platon effect, because this is 0.5 d and this side 0.5 d. So, it goes up to 0.86 d. So, Platon effect practically, this effect of restraining effect of the plates works over the whole of the specimen. But if you have a cylinder with h by d is equals to 2, h by d equals to 2 for cylinder. So, in that case what is happening? In that case what is happening? A cylinder h is equals to 2 d, at least this is 2 d, d. The Platon effect will finish up to 0.86 d. So, this is 0.86, 0.86 d and so on. So, there is some portion where you have no Platon effect, it will expand easily, it will expand easily along this direction. So, therefore, we adopt actually h by d equals to 2 and we find the strength is lower, in case of cylinder, strength is lower in case of cylinder, right, strength is lower in case of cylinder. Okay. So, that is it, strength is lower in case of cylinder. Strength result differs for specimen having h by d lower than 1.7. When we ask a question, sometime it is lower, but why it is lower? Some people say buckling. Well, buckling occurs when h by d is greater than 5. So, it is simply because of Platon effect, cylinder strength is lower than cube strength, right. Cylinder strength is lower than cube strength. Effect of h by d ratio decreases with increase in concrete strength as nu by E decreases, sorry, nu by E decreases. So, if you have higher strength concrete, E is more, nu is also relatively, nu by E will be higher for higher strength concrete. So, this nu by E increases, basically the depending upon this of the concrete itself, because expansion of the concrete is important, right. In weak concrete, restraining effect will be more, because it wants to expand, but then if you are not allowing it, so this effect will be more, and you can see how the capping material has actually affected it. So, that is why this depending upon the strength of the concrete, relative motion of the concrete with respect to the capping material, that would differ. and that is what it is. So, cylinder, then failure of the cylinder, you will always see vertical cracks somewhere. You might see something of this kind, right, you might see something of this kind, and you might see something of this sort of thing. So, you see cylinder failure pattern is something of this kind, cylinder failure pattern is something of this kind, all right. So, that is because same this portion there is hardly any Platon effect, and therefore, it shows vertical failure pattern. People have done some experiment, and it has been observed as you increase the h by d ratio, height to diameter ratio, relative strength, if this I am calling 2, I am calling as 1, you know, at 2 it is 1, 2 it is 1, at 2 it is 1, sorry, at 2 it is 1, it is 1 at 2. At 0.5 L by D ratio it is something like this, and it also depends upon the strength. For example, higher the strength behavior is somewhere here, lower strength behavior is somewhere here. So, this effect 1.4 L by D equals to 1, let us say L by D equals to 1, you get about 1 point, depending upon the strength you get 1 point, some cases might get around 1.3, some 3.5 or something, some cases you can get very close to 1.2 and so on and so forth. So, depending upon the situation, depending upon the strength, this ratio, this is for cube or cylinder having L by D ratio is to 1, cylinder having S. So, some experiment shows how it changes actually, but beyond what is observed is that beyond certain point the variation is very little, this variation is little, right. So, that is because of the L by D ratio effect. Similarly, if you have if you just have a kind of a situation where you have put in some packing between earlier one is H by D ratio related to H by D ratio, earlier this was related to H by D ratio, we have changed. So, we have said that if the H by D ratio is high, Platon effect reduces and therefore, strength tends to become similar. Now, if I put some packing, same aspects of capping actually, first case is no packing, second case is 8 millimeter soft boards, and this is 2.4 millimeter plastic board, all right. So, in this case there is no effect, practically you do not see, relative strength almost similar 100, and in case of one no packing, the effect is there. So, packing would affect this, packing would change, cause change, some cases L by D ratio effect could be nullified by putting right kind of packing, but one does not want to do that, we want to standardize everything and use the use the rest, I mean use compare for comparing, the test result for comparing only. So, with less stiff packing, effect of H by D vanishes as in the case of plastic board, because plastic board has got low modulus of elasticity and high Poisson's ratio. So, nu by E is now actually large. So, it can deform itself and allow the concrete to expand, and therefore, this effect is simply not there, it is very little maybe. So, this is what L by D ratio, cylinder to strength and all that. So, therefore, when you are measuring cores, let us say, if you are measuring core, as I said sometime we do testing of core. So, you are measuring the strength of the core and different H by D ratio is there. If you consider this as 1, American Society of Testing Material, the factor, correction factor for 2 is, if it is 2 is 1, correction factor for 1 is 0.91. That means, the cylinder with a L by D ratio equals to 1 would exhibit nearly 90% of the strength, not nearly 90%, exhibit higher strength. So, multiplying factor is 0.91. So, convert the cylinder cube, convert the L by D ratio 1, L, this is L, this is D. So, convert L by D ratio 1 cylinders, strength obtained for L by D ratio 1 cylinder to L by D ratio 2. What you do? You multiply this by 0.91. So, you can see the strength is higher by 1 by 0.91, around 10-11% higher according to ASTM code. I mean, this is of course judgmental, If you see British code, it is 1 by 0.92, Indian standard 516.89. So, everybody takes somewhat lower value. That is for of course core. Now, ASTM gives you the same thing. If I plot it, I get for ASTM, and this is the Indian standard 516. Same thing given in a curvature form. 2.5 above and all that, you would find much of a variation. Above 2 practically there is no variation, and that is it. Now, a lot of people have actually tried to find out ratio to cylinder, ratio of cylinder strength to cube strength, right. So, strength of the cylinder to cube strength on this side, at what point they are same. So, obviously, it will show scatter, large scatter, but typically what we do is, it would vary upon the strength, it varies with the strength. Higher the strength, the ratio is increasing actually relative cylinder to cube strength, because we said that the capping and platen effect, all these are function of the strength as well. But what we do is normally in general we use 0.8 as a ratio of cylinder to cube strength. So, specimen shape has got a role, capping has got a role. Therefore, while Indian standard uses cube 15 centimeter of the side length, some other places they use 15 centimeter dia cylinder, their strength would not be same. So, it depends upon specimen type, L by D ratio, and also we have seen what kind of capping that you are using. So, long cracks initiate fracture earlier in a larger specimen. Therefore, now size is the other issue, dimension of the specimen. If the specimen size is large, then it fails at lower load. Why? Because long crack initiate fracture earlier. So, in a larger specimen, you are likely to find out a longer crack or longer fissure right in the beginning, right, and therefore, in a larger specimen one is likely to find longer crack, thus lower strength results. So, this is somewhat something called size effect sort of thing. Larger the size, lesser is the strength. Experimental data for cylinder exhibit reduction in strength compared to 150 mm specimen for larger diameter. So, if one does systematically, but then the error is so much in our normal testing, the variation, capturing the variation is not very easy. You have to do a lot of tests actually. For example, just doing 3 cube of 10 centimeter side length, 3 cube of side length 150 mm, and 3 cube of side length, let us say 200 mm. So, 9 cubes you test, 3 of each size, and find out the mean. You may not find the variation, because the error in the tests otherwise, because of all those all the factors that is involved, may just simply mask the effect of this size. But if you do large number of tests, then this effect you do see. So, people have done some testing and they have observed for cylinder and cubes as well. Let us see what are this. For cylinder, it has been observed that if you have larger diameter, if you have diameter increasing along this direction in millimeter, diameter in millimeter, the relative strength, assuming that your 100 corresponds to somewhere 200, I mean 150, sorry, 100 corresponds to 150 mm cylinder. So, relative strength, if the size is smaller, strength is higher, size is larger, but beyond 400 and 500 mm diameter, strength does not change, because the crack sizes are unlikely to increase. So, this is the observation for cylinder. So, you can that is why size is standardized again. Cubes, of course, people have some results are available. Say size of side length, if it is 70 mm, then relative strength is 1.0, 100 to 150 mm. People have seen that it is 1, 200 maybe 0.95, 300 0.90. So, you can see the size of the cube is important. So, if you are using 150 mm cube size, which we standard we use, that cannot be compared with any other size. Now, some of the codes, some of the European codes or Euro codes, they actually allow you to test different sizes. Many countries they allow you to test actually different sizes of the cubes, but one thing, it is only for comparison purpose and same size. Supposing I am comparing 100, I am using 100 mm cube, then I must be comparing different concrete with 100 cube only. Laboratory, standard, of course, standard for quality control and acceptance, etc. In Indian scenario, we use 150 cube, but in laboratory sometime people might do it 100 cube, but then 100 cube has to be translated to 150 cube results. It is not same. Similarly, cylinder somebody might use 100 by 200 dia, 200 length, h equals 200, or somebody might use 150 and 300, which is standard in many countries, but then comparison will be 100 dia to 100 dia, 150 dia to 150 dia. So, that size is important. So, this is the other test factor, which is very, very important. Then next important thing is the rate of loading. Higher loading rate yields higher strength. Quickly you load it at a very faster pace. The fracture do not transmit so easily, it takes time. While you just put a sustained load, there will be effect of creep in an extreme case. So, some deformation might occur with time, all right. So, you see, sustain, if you are monotonically increasing at a very slow pace, the strength observed will be less compared to if you are doing it at a fast rate. So, loading rate is also important, and this many people seems to miss it. So, your test specimen, cube test specimen used in concrete construction, when tested, the testing machine must have a mechanism to control the rate, right. So, ultimate strain is attained early at a lower rate of loading due to creep. That is what we are saying, that supposing we assume that strain is where it fails, fracture occurs, and it will occur at. So, rate of loading has a relation, kind of effect on strength. For example, strain rate per second, if you put it, then measured strength. So, higher strain rate, strength increases, lower strain rate, strength decreases. Similarly, loading, if you see relative measures, higher rate of loading, load per second, let us say, load applied per seconds, or let me put it this way, load per second, relative values, the relative strength increases. So, at higher rate of loading, whether it is strain controlled situation or you are controlling the load, the rate of load application, because they are not same thing, load control and strain control are different. Load is easily controlled by hydraulic system, while a strain control would require you are finally actually applying load, but then you want to control the strain. So, you have to measure the strain, and there is a feedback loop through which you see that the load is changed. So, it requires a kind of controller. Okay, we will not go into that right now, but whatever it is, rate of loading is important. Higher rate of loading tends to show higher strength, higher rate of loading tends to show higher strength. So, therefore, what codes have done? Indian code uses 14 MPa per minute as the rate for cube and 12 MPa per minute for cylinder. So, basically this is by and large worldwide similar sort of things are used. 14 MPa per minute rate of loading is used, and this is very important in quality control, because the machine must have this capability to control this, and that is quite often one has to check this in case of acceptance of concrete, etc. Moisture condition, moist specimen lower the compressive strength than dry specimen. I just mentioned it other day, because if there is an adsorbed water. Now, what is adsorbed water? Adsorbed water, vapor can be adsorbed, that forms actually a layer. As you know, water is dipole, H O H. So, center of positive charge is here, negative charge is here, this is 105 degree or some such angle, whatever the angle is. So, this is not 180 for surely. So, H here. So, therefore, it can form a dipole, and this water can get attached to the charged solid surfaces in case of very fine particle like clay or cement gel, cement hydrate gel. They are adsorbed waters. We talked of this sometime earlier, right in the beginning. So, this adsorbed water causes dilation of cement gel, lowering cohesion, resulting in lower strength. So, it is adsorbed water. If you have moisture water, adsorbed water is by capillary suction. So, even capillary suction absorbed water, the water that goes in, that also results in lowering of cohesion, because it is get absorbed by surface tension forces. So, change in the surface energy and all that occur, and that results in lower strength. So, thus cubes are to be tested at a standard moisture condition. So, you have a saturated surface dry situation, and the code tells you within how much time you should wipe off the surface and then test it, and put wipe off the surface, put it onto the exposed for certain period of time, and within how much period of time actually you should be testing. So, moisture condition is an important issue. So, that is what we have. So, what we have seen for cube, first of all we have seen the capping and size, I mean aspect ratio, I will say L by D or H by D. Then we have seen rate of loading, moisture condition, size of the specimen. So, all these factors affects the strength. Therefore, codes standardizes those condition, and except the material, the composition, the concrete that is produced. So, therefore, I can compare relatively the material that has, or the composition that has gone into making of the concrete. The concrete that is produced as a material. So, concrete materials is relative performance in terms of strength can be compared by cube test or similar sort of things. So, let us look at tensile strength. How do we measure tensile strength? It is actually difficult to measure tensile strength directly. I mean, one can use what is called a Beckett test, something of this kind specimen. Directly, but gripping this specimen is fairly complicated. You have to grip it here and pull. If there is any horizontal load, any moment or anything of that kind coming in, that can create problem and just cause it to fail here. May not be failure, is a tensile failure. So, pulling it and all that. So, there is some amount of complicacy involved. Therefore, this test is not done. This test is not a preferred test. This test is not a preferred test for concrete tensile strength, and direct tensile strength is rarely used also. So, what we use, of course, sometime we use, but let us see, we have better method. Since we have better method, we use that better method or easier method, I will say. In case of flexure, of course, it is not direct tension, tension in some part, compression is some part, all right. Direct tension is full specimen is under tension. In case of flexure, full specimen is not under tension, only a part, tensile stresses also varies, we will see that. So, this strength, tensile strength in failure, we test by what is called modulus of rupture test, right. We do modulus of rupture test. Then for direct split tension test is done, but this itself is an indirect test. Indirectly we measure the direct tensile strength of concrete. So, this is called split test, split tension test, Brazilian split tension test, and so on and so forth. In case of modulus of rupture, what we do? We have the beam specimen, right, and then this supported on 2 rollers. So, this is 3D. So, this spacing is same, and load is applied to 2 rollers p by 2 p by 2. So, you apply actually p here. Generally, this is 50 centimeter total, 50 centimeter as per IS. This is 40. So, 13.3 you apply the load, and this is d dash, this is some dimension depth, this is d, this is b, and this is d dash, usually square 10 by 10. So, d dash is equals to b, you can apply sometime, but not necessarily, you can but the principle does not require this. So, loading rollers capable of rotation and inclination in the vertical plane. That means, you are only transmitting downward force, because they are roller point loads, you are only transmitting point loads. So, if in case this bends, this is capable of rotation and getting inclined in the vertical plane. So, therefore, this will not apply any other kind of force except for this type of force, and these are the supports. So, supporting roller capable of rotation and inclination in the vertical plane, same thing. So, it will only give you point load. So, actually you are trying to put a point load, and that is how it is. So, what will happen? I will have a bending moment diagram of this form, P by 2 here, L by 3, of course, this from the center L by 6 and 3 by L. So, your bending moment here is L by 3 into P by 2, So, this will be bending moment will be simply P by 2 into L by 3, which is equals to P L by 6, and the maximum stress Z value is given as you know, is moment of resistance will come out to be P L by B D square, because this will be Z, the Z section modulus is B D cube by 12 and D by 2. So, this will be simply B D square by 6, and therefore, m by Z will be P L by B D square. So, that is the at failure you find out what is the P value at failure, and the corresponding F value is called modulus of rupture, MOR, modulus of rupture. It is actually a measure of the flexural strength, MOR, modulus of rupture is a flexural strength, right. Now, why do we choose this? Bending moment is constant here, simply 0 shear stress. Shear diagram, if I look at it, it would be something like this, or so there will be no shear stress, shear force here, there will be no shear force here. So, I am trying to actually minimize the shear stress and only bending moment. So, it is a pure flexure within this zone. Then also the if it is a single point loading, you will have only one point, failure may not have occurred within that. So, here you are increasing the chance of failure due to pure flexure by putting 2 point loading. So, no shear force, pure flexure, and so on and so forth. Now, people do, of course, if you have different dimensions, case 1 is single point loading, case 2 is 2 point loading, the variation is there, but I said this is what is standardized, 2 point loading has been standardized. Obviously, it will change with the dimension like we did for said for cubes. You see, modulus of rupture value that I am calculating, I am assuming the stress diagram is like this, that P L by B D square that I obtain. I assume the stress diagram is linear, but real stress diagram will be something like this. So, you see, MOR actually overestimates the result a little bit. The 2 point loading ensures pure bending without shear in the central 1/3, that is what I said, and 2 point loading produces maximum moment between the loads, thus more area is exposed to maximum bending moment than 1 point loading, hence lower apparent modulus of rupture. Calculation of MOR assumes triangular stress distribution, actual stress distribution is different. So, modulus of rupture is therefore, it overestimates even the flexural strength, but we will see that the other kind of test results, that is split tension test, that we will do, that we will just discuss, gives you lower strength than modulus of rupture, but if you are able to do direct tension, that will give you still lower. All right. So, what is split tension test? So, this is what it is, tensile strength, modulus of rupture, this is of course direct. So, this in linear, of course, they are linearly related, but this is always lower, this is not a line here, not 45-degree line, this is somewhere here. So, when this is 1, this gives you somewhat higher value. So, this direct tensile strength or tensile strength is usually lower. This is how we do split tension test. You apply load like this on a cylinder, point along the line, or I can say something like this sort of load here over a small area P, and if you take the stress at any point, that stress can be drawn from theory of elasticity. These stresses are available, concepts are available, and this stress diagram one would look like this, where this is your compression, this is the tension. So, only top small portion there is a compressive load, because we are applying compression here. We are applying compression here. So, only small portion there is compression, rest of the portion it is actually tension. So, it is trying to split along this direction. So, this portion is only compression, and you can see it is because of the shape of it, or the kind of the load you have applied. So, it is seen that this is only portion where compression is applied, most of the portion you apply actually tension, trying to split. So, d by 6, d by maybe d by 0 to 6 and 12, maybe d by 12 or something, d by 12 or somewhere close to that. All other places it is actually tension. So, the F t, this is F t, F t is given as this F t is given as twice P by pi L d, where P is the load that you have applied, pi L is the length, L is this length, L is this length, L is this length. So, this is L, this is d. So, 2 P by pi L d is a, at failure, P failure, if you take P maximum, this will be your tensile strength, this will be your tensile strength. So, split tension test gives you, you can do it on a cube also. In that case, it will be like this, you apply P here, and the formula is F t is equals to twice P by pi d square. This gives you lower strength than modulus of rupture, this gives you lower strength than modulus of rupture, because in case of modulus of rupture, only the bottom fiber is subjected to maximum tension, other are not. Besides that, you are actually overestimating, you do not take actual stress strain diagram. Split shows lower strength and direct tensile strength will show still lower, because in split at least there is some compression portion. Non-uniform stress distribution in MOR, that is modulus of rupture, and split test impedes the propagation of crack, thus delay failure, therefore, this is the case. We have discussed this. Crushed aggregate exhibit better modulus of rupture than rounded aggregate, and because of bond of moisture condition also bond. So, bond is very important in this one split. So, crushed aggregate with rough surface actually. So, some or other here this shows better modulus of undulation would be there in case of crushed aggregate. Rounded aggregate, this surfaces they might show split might differ. Moisture condition also influences. Now, it influences in a different manner. Moisture condition influences in a different manner. How does it influence? Higher moisture content shows, I think I have shown the diagram earlier, higher moisture content actually shows higher tensile strength, unlike compressive strength. Why? Because it minimizes the shrinkage, while dry specimen shrinkage comes into picture. So, this is because of shrinkage, shrinkage, this is in this case it is because of shrinkage comes into picture. So, in case of dry specimen there are some shrinkage cracks which will always be available, and the tensile strength becomes lower, both MOR as well as the direct tensile strength. So, moisture condition, aggregate type, everything affects this, and therefore, what we have seen compressive strength, the effect of test factors L by D, H by D, capping size, rate of loading, and we have seen also finally, I would like to say that it is a relative measure of the strength of potential mix, that is what it is. And tensile strength, this also varies with the type of measurement. Modulus of rupture gives you higher value. Code of course uses different one, which we have which we will be talking about in the next class sometime, how the or I think we have talked about this actually. The code gives you 0.7 under root FCK. So, these are based for relative for use in design. So, there are some conservative value, but test conditions how it affects, that is what we have seen. So, I think we can with this we can close our discussion on this third lecture for the module 6. Thank you very much, and we will be looking at modulus of elasticity and other mechanical properties of concrete in the fourth lecture of the 6th module. Thanks.